आज की शाम में आप सभी सुधीजनों का स्वागत एवं अभिनंदन. Very good evening to all of you who are present in this hall. So maybe now we are going to formally start this function itself. So I'll request the dignitaries to take the seat on the dais. But before you take the seat on the dais, like maybe just offer your floral tribute to Mahavana ji, founder of this institute and the university. I'll request S.K. Sharma ji to kindly escort chief guest Professor D.N. Agrawal ji, our officiating director G.V.S. Sastry ji, and Dean Resource and Alumni Professor Anil Kumar Tripathi ji. I'll request Professor G.V.S. Sastry, Officiating Director, to felicitate our Honorable Chief Guest, Professor D.N. Agrawal ji, by presenting him a flower bouquet. Thank you. I'll request our Dean Resource and Alumni, Professor Anil Kumar Tripathi ji, to deliver welcome speech. Professor Anil Kumar Tripathi ji.
Honorable Professor G.V.S. Sastry, Director of the Institute today, and Dean Academic Affairs, Professor Brij and Agrawal ji, distinguished alumnus of our institute, Professor S.K. Sharma, Chairman of the Institute Lecture Series, Professor A.K. Agrawal ji, Associate Dean of Faculty Affairs, Head Department of Mechanical Engineering, and one of the organizers of the Institute Lecture Series. It is a very proud moment, and I am very happy that I am here again sharing dais with Professor Brij Agrawal ji. We happened to be together at the time of IIT BHU Global Alumni Association meet in September there at Santa Clara in California, where some 400 people, alumni, gathered. And again today he is here to be with us and to deliver the coveted institute lecture today. Professor Brij Agrawal is a very famous academician on the globe. He is associated with the Naval Postgraduate School. He has been responsible for establishing great centers of learning. He is currently distinguished professor at the Department of Mechanical and Aerospace Engineering of Naval Postgraduate School and director of Spacecraft Research and Design Center. Happened to be director of Adaptive Optics Center of Excellence also. During the first alumni meet of the institute, and this happened during the centenary year of Banaras University, we had identified Dr. Brij Agrawal ji as recipient of the Distinguished Alumnus Award for Academic Excellence. We identified other people also. It happened so that Professor Agrawal could not make to that alumni meet. So we thought fit that we would be having a lecture to be delivered by him here in the institute, and at that time we would be decorating him with the Distinguished Alumnus Award of IIT BHU. So that is the type of occasion that we have today. It is a great day that we are having Dr. Brij Agrawal ji to deliver a lecture. He will be decorated with the Distinguished Alumnus Award, and he will be launching some discussion activities for the Technex as well. I am here to welcome Professor Brij Agrawal ji on behalf of the fraternity of students and staff and at the same time from the fraternity of alumni spread world over. So I heartily welcome you, sir, Professor Agrawal, to be with us. You will be a great source of inspiration to our students and colleagues for all times to come. And I now ask Professor Agrawal to kindly continue.
Thank you, Professor Tripathi ji. He has given brief about our chief guest today itself, but whatever has been said about Professor Brij Agrawal is just maybe tip of the iceberg. Maybe if you read his biodata, of course, maybe you are going to present the citation for him itself. That of course it goes in one page. But if you read about all his contribution, it will take about an hour just to maybe read the summary part of it. So he has that much of contribution. So we are very lucky and we are very fortunate to honor and to recognize the effort of our own alumnus, Professor Brij Agrawal, and rightly said by, we are going to decorate him with Distinguished Alumnus Award. And the second most important thing is, the person who is being given this kind of distinguished award, we are very lucky to hear from him. He is the third alumnus to deliver institute lecture. So we are very fortunate. First one happened to be Professor Manu Vora ji, Dr. Manu Vora. Second one, Padma Shri, SP Sukhatme ji. And we are very fortunate to have the third lecture again from our own alumnus, Professor Brij Agrawal. Now maybe I'll request Dean Resource and Alumni to kindly bring our chief guest, Professor Brij Agrawal, in the front of the dais. And maybe I'll request our officiating director also to give him a company. I'm going to read out his citation itself just to give you a glimpse of the kind of contribution that he has made for we people and for the world in general. Professor Brij Agrawal is internationally renowned for his excellent contribution to all aspects of space engineering, including establishment of centers of excellence and unique laboratories. He is currently Distinguished Professor, Department of Mechanical and Aerospace Engineering, and Director of Spacecraft Research and Design Center, and also the Director of Adaptive Optics Center of Excellence. He earned his BSc Mechanical Engineering degree with honors from this institute in 1964, ME with honors again from IIT Roorkee, MS from McMaster University, and PhD from Syracuse University. He joined Communication Satellite Corporation ComSat in 1969 and International Telecommunication Satellite Intelsat in 1979. During 20 years at ComSat and Intelsat, he participated in the development of several communication satellites and developed several new technologies for fine spacecraft pointing and got a US patent for the same. Sorry. He has also worked on aeronautical courses in industries and universities in USA and Europe. He has also worked on aeronautical satellite program. During his stay for 1 year at European Space and Technology Center in Holland, he wrote first book on design of geosynchronous spacecraft, an internationally popular book for universities, including MIT and Stanford University, and also for space industry. In 1989, Dr. Agrawal joined Naval Postgraduate School as a full-time professor to develop astronautics program. Within a year, he initiated new MS degree program in astronautical engineering, developing several new courses and advising thesis work of PhD and MS students in the spacecraft quanting. He has taught courses at industries and at Stanford University on spacecraft design. He founded the Spacecraft Research and Design Center, SRDC, including 5 unique state-of-the-art laboratories. He had been involved in the development of several state-of-the-art military spacecraft and made exceptional pioneering contribution in the spacecraft fine quanting for imaging spacecraft. His expertise for commercial spacecraft was also soft. Professor Agrawal envisioned and established the Adaptive Optics Center of Excellence in January 2011, having a sponsorship worth $3 million per year from 3 agencies. This year has resulted in unique testbed in USA for imaging satellites and high energy laser and new technologies. He has published over 150 technical papers and received 2 US patents. He has been thesis advisor to 10 PhD students and 50 MS students. He had 15 postdoctoral fellows working with him on research. He has given short courses in space system and adaptive optics at Defense Research and Development Organization DRDO here in India, and is working currently on a multi-layer project on the application of adaptive optics to correct the high energy laser beam aberration due to air turbulence. He has been associated with Indian Space Research Organization ISRO right from the time of development of INSAT-1. He is Fellow of American Institute of Aeronautics and Astronautics AIAA and was elected as a convener of International Academy of Astronautics. He received AIAA Spacecraft Design Awards. He was honored as Distinguished Professor at NPS, receiving several teaching and research awards. He received Navy Superior Service Award. He also received Intelsat Award for inventiveness and technological contributions. In summary, Professor Agrawal has made exceptional contribution in multidimensional aspects of satellites, research, development, text, book writing, technical papers, patents, educating young engineers and research fellows, setting up of new astronautics program and centers of excellence. His accomplishments are due to his incredible ingenuity, innovation, leadership, hard work, drive to excel, and dedication to the organizations he has worked with. In recognition of his significant, exceptional, and long contributions to teaching and research in space engineering, the Institute is proud to felicitate Professor Brij by conferring on him the Distinguished Alumnus Award Academic in the centenary year of Banaras University and the first alumni meet of IIT BHU Varanasi. I request now the officiating director to present him citation and memento and song also. Thank you, Sastry ji. Now I'll call upon Professor Sanjay Kumar Sharma ji, who is chairing this Institute lecture series, to tell us something about Institute lecture itself, and I will be requesting our chief guest formally to deliver today's lecture. Professor Sanjay Kumar Sharma.
Honorable Professor Brij and Agrawal, our distinguished alumnus, and the 26th speaker of Institute Lecture Series, Professor G.V.S. Sastry, our director for the day, Professor Anil Kumar Tripathi, Dean, Resource and Alumni, Professor Anil Kumar Agrawal, my senior colleague, head mechanical, and member, very dynamic member of the Institute Lecture Series Committee, and Associate Dean of Faculty Affairs. So in multiple capacities he has been helping us. This series was established when we converted ourselves from Institute of Technology to Indian Institute of Technology, Banaras Hindu University, Varanasi, on 29th June 2012. I just want to give you a brief summary for those of you who are joining us for the first time. We had a basic punchline when we started this series, and that was educate to innovate and innovate to change. Education by itself should have an objective for innovation. Innovation, Professor Raju Sangal says, is nothing but putting research into right context. So most of the speakers that we have tried to bring amongst our student and faculty fraternity, institute fraternity, have contributed meaningfully to the society by their own efforts, and they have gone beyond textbooks. And if you see most of our speakers, their speeches are now video recorded and are available in Institute Twitter account, that is ILS at IIT BHU, ILS IIT BHU. If you go there, all the video recording links are there, and many of the people are viewing it. So I don't bother about the numbers who are physically present over here, because after each lecture I find most of your video recorded lectures are viewed by people from abroad. Our alumni are saying that they want to listen to institute lectures, and therefore we have made it particular that all the videos are put on YouTube and their links are available on Facebook and in Twitter, and very soon I am going to have a LinkedIn account also. So what Vivekanand used to say, that if Muhammad cannot come to mountain, let mountain go to Muhammad. So we are to facilitating the opinions and the works of these doyens of their field. Means while I was going through the biodata of Professor Agrawal, I also have given you a link of his website. And there when I was just doing the pull down menu, when I came across, there is a concept in education of Dronacharya. So Dronacharya was providing structured education to all the students who had enrolled themselves. But those who wanted to get educated from Dronacharya but were not able to afford the registration fee and all, they became Eklavya. And Eklavya also got inspired through Dronacharya and reached same level as was reached by Arjun. So these people who are delivering institute lectures, you can be Eklavyas for them, get inspired from them, get pedagogy from us, and get all the backup from us. And these people can inspire you in the long range. And when they are coming to their alma mater, probably they are giving their one of the best that we have seen. All the alumni have simply given us gems, and those of you who are not here are missing. I am not sorry for them. I am sorry for them only because that they are missing the live presentation of such classical lectures. Video lectures cannot be substitute for the live lectures. So I'll just add upon Professor Anil Agrawal's statement that he is probably the fourth alumnus. Professor Raina was missed by Professor Agrawal. Professor Raina, V.K. Raina, is also a celebrity in civil engineering. If you just type on Google V.K. Raina, you'll get, he is an authority on Brij. And when I requested him to deliver an institute lecture in 45 minutes, he said, it cannot be done. I need 4 hours. So the institute debated with Professor Raina, Dr. Raina for many weeks. He used to say, I cannot do any justice to bridge engineering without deliberating for 4 hours. When I go to College of Pune, the whole college stops. Principal sits with me and I talk for 4 hours. So in my alma mater, I cannot do anything less than 4 hours. So he took 2 hours in one session and we gave him another on the next day. So for 4 hours, he was an alumni, he had every right to demand what he wants. So we have the love and affection of the alumnus, it is that which brings them here. Otherwise, the way we are treating them and the level of troubles that they are facing would surely, I'll say, discourage them. जो देश ने इनके साथ किया कलाएं हैं, अमेरिका से आए, उसके बाद विस्तारा बनारस लाते लाते 3 घंटा लेट कर दी. उसके बाद ऐसे समय में सर आए हैं जब नोटबंदी चल रहा है. तो सर भारत के नोटों के साथ आप भारत में ऐसे रह रहे हैं जैसे विदेशों में है. आपका नोट चल नहीं रहा है और जो बैंक से निकल भी रहा है वो 2000 का. सर का जो कोई भी जो वेस्टर्न मनी वगैरह सब ठप पड़ा है इस समय. ऐसे समय में सर हम लोगों के बीच आए हैं और हमारे अग्रज हैं, और सर ने दूसरी दुनिया, मतलब अगर अमेरिका देखें तो ठीक उल्टा है भारत के, जिसको पाताल कहते थे हम लोग, वहां जाकर सर ने स्टैब्लिश किया है खुद को, और नॉट ओनली खुद को बट एक नए सब्जेक्ट को, सैटेलाइट साइंस पूरा का पूरा, फॉर राइटिंग फर्स्ट टेक्स्ट बुक. Those of us who are attempting to write books understand what is the difficulty in writing first textbook. You have to define every word. You have to come out with terminology which is non-ambiguous, which is acceptable universally. And after he has done the first textbook, revision is very easy. Criticism is very easy. But writing first textbook is a landmark activity done in any subject and establishing that subject. He has full credentials, highly awarded. जितना अवार्ड सर को मिला है सब लिस्ट नहीं किया जा सकता, बट बहुत सारा अवार्ड मिला. सर ने काम भी किया, रिकॉग्निशन भी लिया, और उसके बाद अपने अफेक्शन से हमारे बीच आज है. और ऐसे ही 25 we have made silver jubilee. Last lecture was silver 25th one, and Abhay Bang, Dr. Abhay Bang, who delivered it, he had, when Lancet is one of the most reputed journal in the field of medical science, and Lancet, when it wrote its history and published few of the papers that they called it landmark, Abhay Bang's one paper was there in that. So previous speaker was also equally illustrious. We have had 25 of them. The institute is lucky, let me tell you, to bring that much of knowledge and so great speakers amongst you. We have so far not asked our faculty members to join it, though they have been delivering elsewhere. But because they are homegrown, on home ground, we have not asked them. So probably in future we might try. This series is absolutely for the whole institute fraternity. There is no restriction of whether it is for students or faculty, and I'll say virtually we are present all time. So I invoke those of you who are here to tell your friends to visit our, we'll soon have websites also, and our other links to get what these people have said, so that you are inspired. And on inspiration, you can do much better than a routine uninspired soul does. With that, I request Professor Brij and Agrawal to deliver the institute lecture for today.
Kindly congratulate on our behalf Professor Agrawal on decoration with this distinguished celebration.
Sir, on behalf of the Indian Institute of Technology fraternity and on my own behalf and all the alumnus, getting awarded in the first alumni meet itself is a historic achievement of this institute, which has about 10,000 alumni. So I congratulate sir for it, and I now invite him for delivering the institute lecture.
Professor Sastry, Professor Sharma, Professor Tripathi, Professor Agrawal, other faculty, students. Actually, it is a great honor to receive award from your alma mater. It's like getting a reward from family. And it was a big surprise to me. I was completely surprised. So I feel very grateful for this recognition. And thank you for going through what I've done. And I think I've been to other universities like IIT Roorkee, McMaster, Syracuse, but Banco, as it was known at our time, IIT BHU, is very close to my heart. And actually the architecture here, like a temple. So whenever I feel like a BHU sick, I normally go to Stanford University because it is also somewhat very similar. And I think what I am, I think BHU has made a major contribution. Yeah, when I came here in 1960, I was youngest in my class. I came after intermediate, and more than 50% came after BSc and some MSc. And then I came from a small town, and here it was from all over India, Delhi, Bombay. They spoke very good English. And at our place, even English teacher could not speak fluent English. So there was, then on the first day, I was asked to go to some room. So ragging was very common during that time. So it was quite a challenge. Then we used to take about 12 courses And if you fail in one course, you have to repeat the whole year. So we were very much challenged, but at the same time, it was a big honor to be admitted to BHU Bangkok. So we basically worked very hard, and then I, as I said, was very challenged. But then I got a good rank in first year, and that provided me a confidence that if I can succeed here, I can succeed any place. And that really has helped me because I love taking challenge and make it a success. And I think that is an important part that one should learn. Now today I'm going to talk about this topic. I wonder how many of you have heard about adaptive optics? Probably not many. I also did not know about adaptive optics 15 years back. So it was kind of new to me, but I like challenge. And I started getting into this field, and I was surprised that we got Center of Excellence in Adaptive Optics supported by 3 organizations. So I think never really hesitate to take challenge. Now I know it is 5 o'clock, after 5 o'clock, so you must be almost 5:45, so you must be all tired after taking all the courses, lectures and all that. So I've tried to make this presentation not too boring. I hope you will like. I've included some of the videos, so you will see our laboratories and so on. They're not, I think there is only one slide with equations, so there are no equations to really get stress out. So let us see how it goes. So basically these are outline of my talk. So one, I will talk about large aperture imaging satellite. That is something right now in space imaging most challenging, because we want a large aperture imaging satellite so you can get a good resolution of the images from the ground, but it becomes quite challenging. Second is area, which is if you have a laser beam and you are going through atmosphere, it gets distorted. So how to correct that laser beam? So that is, you can use adaptive optics for doing that. And that is the area, actually, we have a joint project between US and DRDO. And I'm principal investigator of adaptive optics in that area. Most of the research actually is becoming very multidisciplinary. So here in this our group, we got people in structures, controls, optics. They are expert in their own area, but then they work together, and that is how we are able to do research and develop things. So actually, we have quite a good size group. So let me explain you what is adaptive optics. Now, if you have let us say you got a planet and you got a telescope on the ground. So you have that target, or that is coming, your image is coming, but then it gets distorted by atmosphere. So on the ground, if you put a camera, you will not get a very good picture. So we want to eliminate the impact of the atmosphere on the image. So what we do is, he created another reference laser beam, and it will be going through the atmosphere. So you got a clean beam, it get distorted.
Very challenging problem.
So now you got a sensor, you measure the distortion in the beam. Because it won't be collimated, you will have distorted beam. So you can measure it by sensor, and then you got a deformable mirror or adaptive mirror. Here you can change the shape of the mirror. So basically, if you got a distortion in one direction, you want to distort your mirror in the opposite direction. So when you combine it, your distortion is gone. So you basically have a reference beam, you go through this wavefront sensor, you keep on changing it till the error in the wavefront sensor is eliminated. So now if you got your image coming from planet, it gets distorted, then it gets corrected, and then you get a nice picture on your telescope. So basically, if you think about in adaptive optics, you got a mirror where you can change the shape of the mirror. So then in the back, you have actuators like a piezoelectric actuators and so on. So you can change the shape of your mirror. So that is the one element. Second is you got a sensor which can measure the distortion, and then you have a control loss. Based on the error, you come out how much voltage you should apply to those actuators. So it is a multidisciplinary. It is optics, it is the structures, it is the control and dynamics. So that is where, like I was more in the controls and dynamics and spacecraft, and not much in the optics. But that was only one element. So I decided let us take a challenge and go for that. So these are kind of a sensor. You got a light which is coming, it is a plane wave, and here you got a lenselet, and you will get focus these points, and they will be equally spaced. Now when you get distorted, then you got a slope, different slope. So they will be getting this point source at different points. They will not be equally spaced. And you measure the error, where it should be, and based on that, you can determine your distortion. Here you can see that here they are all same angle, here different angles. And so these are different kind of deformable mirrors, and there are membrane deformable mirror, and it is electrostatic. Then piezoelectric, you can apply voltages, so you can distort this surface, and there are segments and all that. So we have a lot of instruments, the deformable mirror in our labs. Here you can see that you got this image, and due to atmosphere it gets distorted, and it's not really that good. And this is the image, and then if you put adaptive optics, then you get a nice image. Adaptive optics has many applications. One is ground telescope, and actually this adaptive optics technology up to 15 years back used to be classified, but now it is unclassified, and it is very actively used on the ground telescope. Now you might have heard about James Webb Telescope. This is after Hubble Space Telescope. So this is, they also use some part of the adaptive optics. Now for the laser communication, if you have a laser communication, you get a high capacity. So again, if you go through the atmosphere, it will get distorted. So you can use adaptive optics for correcting for that distortion. And it has other military use. that you got a high energy laser, and if you want to send through the atmosphere, then your beam will be distorted and your intensity will go down. Then you use adaptive optics for correcting it. So it has a many application in the commercial, in educational, and in the military. Now, big problem right now we have for imaging satellite, that we would like to have large mirror, because your resolution depends on the distance and the size of the mirror. If your mirror is bigger, you get a better resolution. And here is kind of a formula. D is the diameter of the mirror, R is the distance, wavelength, and the resolution. So if you want a resolution, means a small resolution. So if this is smaller, then your diameter has to become bigger. But in space we have a problem. We have to put on the launch vehicle, and there is a restriction on the size of the shroud, typically 3-4 meters. So if you want to have any mirror more than that, you have to stow it during launch and then you deploy it. Now, one of the problems of these mirrors is the surface has to be very accurate. We are talking about 30 nanometer RMS error. So you have to build those mirrors very, very accurately. It's a lot of challenges and all that. So it is becoming a very challenging. Secondly, you want to make it light. Our space telescope was 240 kilograms per meter square. In our lab, we have a state-of-the-art mirror telescope, and it is 20 kilograms per meter square. You can see how much lighter it is. But you don't get something for nothing. If it is a lighter, but you don't get a good surface. So we put lot of actuators to correct the error on the surface. And this one is James Webb Telescope. So this is kind of a very challenging problem right now going on. And our group is working in this area using adaptive optics. Now this is the telescope, state of the art, which we have in our lab. And it was quite a challenge. I had to decide whether I should really get that telescope in our lab. It was developed by Lockheed Martin, IIT, in the government program. It is a 3-meter telescope, and it has 6 segments. And as I said, they are very light, like they are 20 kilograms per meter square. So each segment has 156 actuators on the back. So you can correct the surface of the segment of the mirror. So it becomes very complex control problem, how much voltage you should apply to those actuators, how to measure the error, and so on. Then these segments, when you deploy it, they should act like a part of a large mirror. So if there is a phasing error, it has to be corrected. So we got 6 force actuators, 5 actuators for phasing those segments, and these wavefront sensor and so on. And jitter is also very important. If you have a camera and you are moving, then your image will be distorted. So we have to keep those satellite very, very jitter free. So all these are very challenging. They are both mechanical problems, control problems, optics problems, and they are all related. So it is quite exciting. Now, in our lab, we do the testing. This is the telescope, and here we have a 4D interferometer. So we basically send a laser beam and goes to the mirror and comes back. If you don't have any error in your mirror, then the beam coming back will not be distorted. But if this surface is not perfect, then the upcoming beam will be distorted, and then you measure that distortion by interferometer, and then you feed back into actuators so that you can correct it, and you keep on correcting it. and you find out what you call influence coefficient. One actuator, you put one actuator on, and then you find out the distortion in your surface, then second, third, fourth, and so on. So I will not go into. Then it is a control problem that you want to find out, you know the error, and you want to find out the voltage which you should apply to your actuator. And then these actuators have the limit, lower limit of the voltage, upper. So you basically go through the optimization to find out the voltage which you should apply. Now these mirrors are very expensive. Some of them, they take about 2 years to make it. And they are expensive because of the surface. We are talking about 30 nanometer RMS. They have to be polished for a long time. So what we are suggesting is that you reduce the requirement of the surface of the mirror, and then you put a deforming mirror, a small one. So whatever the residual error you have, you can correct it by deforming mirror. So that will make your total system much more cost effective. And secondly, you don't have to do that much testing, because if there is some error, you can correct in orbit. Because that is in space, we spend a lot of money for testing. Because if something goes wrong in space, you can't correct it. So you have to do a lot of testing. Testing for a satellite is almost 30%, 40% of the total cost. So that's where I think we are getting a lot of support. So here we basically put another deforming mirror. So first we correct it by these actuators, and then whatever the residual, we correct by deforming mirror. Here I will give you some numbers of the error. So initially we had 348 nanometer, almost half wavelength, and then we put actuators of those 156 in each segment, and we reduced from 348 to 196. Then we put a deforming mirror. We got many MS and PhD students, and we were able to do 158. So first we corrected there, then deforming mirror. Then we did a lot of optimization, how to combine those two, deforming mirror and segment, and were able to reduce to 113.7. So it is quite a good control problem, optimization problem, structure problem, optics problem. So you have to work as a group, and I think that's where if somebody wants.
Do you go for experiment directly or do some simulation and then go to?
Yeah, we have analytical models. So we basically, whatever we're doing in our research, we got analytical models, and then we got a test bed. So we predict it by the analytical models, and then see it experimentally and correct it. So that's where in my group I insist even PhD students do both. Okay, here is the movie. This will give you some idea about the facility we have. It is quite a large facility. It took a lot of my time and effort. So this is the room. We have this segmented mirror telescope. Now this room is not a standard room, it is a dark room, because you don't want the laser beam to be reflected from your walls. So they are all black. Then you want to have a temperature control, and you would want basically like a clean room. So, and secondly, as I said, jitter is very important. So you put on the vibration isolation table. So there is from the ground, there is no vibration coming, and that becomes very critical because we are talking about very small jitter. Yeah, so this has almost become a VIP. Anybody comes to our place has to visit. This is a PhD student. And this is kind of a unique in US, maybe in the world, for this kind of facility. So it was quite a challenge. So I think that's where one should try to take a challenge, but it is quite. Then you can see there is a lot of optics going through all the mirrors and all that. So we got expert in optics, expert in controls, expert in structure, but they all work like a team, so they're learning from each other.
Do we require to apply some control over deformable mirror, or it works autonomously for deformation?
Yeah, we apply deformable mirror, and it is automatic. You measure the error and then you feedback and you correct it. And you keep on correcting it, so it is an iterative process on that. Now this is the phasing. We want to phase those segments so they act like a part of mirror. So there are like a 6 telescope, and each telescope has a double slit, so the 2 laser beam go one on one segment, other. Now we are also looking into using, most of these mirrors are made of glass, and now we are trying to make them light by using carbon fiber mirrors. Now to give you some idea about these telescopes, you might have heard about Hubble Space Telescope. And this is the one. And we look at these are the dimensions. Now you can see the resolution. Resolution is 0.00001 degree. So you have to really point these satellites very, very, very accurately. And you do not want to have any jitter on the system. And actually this satellite, flexibility has an impact. It has these are the solar panels, this is the telescope. And when they launched first time, they were too flexible. So they were interacting with the control system. So the image was not coming very good. Luckily, they could send the astronauts. They replaced the solar array. And so that's where the structures, controls, optics, they all go together. You have to work like a team. So it is both mechanical, electrical, and physics and all that, and they all come together. Now, another area, as I said, very fine pointing, and you have to have an analytical model, but you want to demonstrate in the laboratory on the ground. And here we got another unique test bed. But the pointing, in space, you do not have effective, you have effective zero gravity, and you don't have any atmosphere. So you want to simulate on the ground. So we got air bearing, and in the air bearing, this representing a spacecraft attitude control system. And air bearing, there is no friction, so it can move without any friction. Second part is you don't want to have effect of the gravity, which will not be there. So you want to balance it, so your center of mass and center of rotation are the same, because then you don't get any torque. So it becomes quite a challenging. Then we got an actuator. Then you got a flexible, like you saw the solar array. So you take one image here, you want to go to the other image, and if your solar array start vibrating, you will not get a good picture till it settles down. So you want to minimize that. So it becomes quite a challenging. You come out with the control laws so that when it goes to the final stage, you do not vibrate. So I have some pictures which I will show you. One, I will show you the bad slew. You are slewing bad slew control system, and second will be a good one. So you can see I am slewing it. And that is one thing we do. Like we have PhD student, they got analytical model, they are predicting something, Then they come to the lab and they want to duplicate. And you can see at the end, these solar rays equivalent, they are vibrating. So that is not good. They are vibrating, you will not get a good pointing. And actually we just, about a week before I left, we got one patent, we submitted for the patent. So we got one patent approved for the slew maneuver. So that's quite a big achievement for the group. So this is the bad slew. Yeah, so sometimes people say, hey, are you going to retire? I say, no, it's still interesting going on. So
These things are not letting you retire.
yeah. So here you can see that we are slowing, but our control law takes into account the frequency, structure frequency of your solar ray. And then you can see at the end, it is quite smooth. You don't see the vibration, and that's where, like, it is, you can talk, but when you show it actually happening, that really helps.
Was that vibration because of improper neutralization of gravity or what?
No, the vibration was that if you apply a torque, you apply a sudden torque, and sudden torque create acceleration. So you want to smooth, then your flexible, they start vibrating. So you want to apply a torque so that you can damp out that vibration. Now jitter is very important. We are talking about like a here, nanoradian. And to give you some example, that let us say if you got a one coin and you put like in India on the your some place which is in Delhi on some tower, and you send a laser beam from here, so your laser beam should stay in that coin. So it is a very, very fine jitter, and we will show you the next slide. We had several PhD students. So we basically had the laser beam coming here, we create a jitter, and then we basically measure it, and then we got this is the other fast steering mirror. So it basically will, here you got the error and it feedback into this mirror and it will correct it. And then we use different control laws, classical control law, adaptive filter, feed forward. So I will not go into details, but I think we have a movie which will, and this has a voice also.
Welcome to the Spacecraft Research and Design Center at the Naval Postgraduate School.
The objective of beam jitter control research is to develop a high-performance control algorithm for an optical beam steering system which is subject to jitter caused by atmospheric turbulence and mechanical vibration. The beam jitter control is very important in many aerospace optical applications. For example, with laser weapon systems or free space laser satellite communication, we need to aim a laser beam at a target which is hundreds or even thousands of miles away. In this case, a tiny angular error of the laser beam's line of sight will result in a large error at target range. Beam jitter control is essential to this application to improve the optical system's performance. This is a laser beam jitter control test bed. Most of the optical components are mounted on a floating table. The floating table is supported by compressed air. The objective of laser beam jitter control is to aim a laser-generated beam to the center of a target sensor. On the laser beam jitter control testbed, the laser beam path is disturbed by two disturbance sources. One is the disturbance fast steering mirror. This mirror has 4 voice coil actuators on its back and provides tip-tilt motion to the laser beam. We use this disturbance mirror to give a broadband disturbance which simulates atmospheric turbulence. The second disturbance source is a pair of inertia actuators. These actuators shape the floating platform and simulate narrowband mechanical vibration such as those from engines, motors, or flexible appendages of the aircraft or spacecraft. In order to attenuate the jitter of the laser beam, we use a mirror called the control fast steering mirror. Using this control fast steering mirror, we are able to reject the disturbance and aim the laser beam to dead center of the target. We also use a position sensor and 3-axis accelerometer to acquire additional data on the disturbance. For control algorithms, we're investigating a variety of different control methods, from a very classic PID control to LQG control to adaptive control techniques. In particular, we are focusing on the adaptive filter control techniques. This technique is very attractive because it can cope with time-varying and uncertain jitter plant characteristics. This algorithm automatically updates its control parameters to some optimal values even though we don't know exact disturbance characteristics or exact system model. In order to show the performance of the developed control algorithms, we've prepared simple demonstrations with the testbed. This window shows a magnified view of the beam location measured at the target sensor. The window size is 1 mm by 1 mm, and the space between each line is 100 micrometers. When I start the demonstration, the laser beam is disrupted by both narrow and broadband disturbances in an uncontrolled manner. You see the laser beam is spread out and moves around off the target. After 5 seconds, the conventional PI controller is activated. You see that the laser beam is now regulated to the center of the target sensor, but that jitter is still present, reducing accuracy. After another 5 seconds, you see the adaptive filter controller engaged, providing greatly improved control performance. The laser beam is now tightly controlled and is directed to the center of the target sensor. This figure shows the root mean square error of the laser beam with the conventional PI controller and the adaptive filter controller. This figure shows the trace of the laser beam. These figures show how effectively the adaptive controller improved the control performance. In the second demonstration, you see the moving target tracking control performance of the adaptive control method. The disturbance is the same, but instead of tracking a stationary target, the laser beam is programmed to track a fast-moving target. In this demonstration, the target moves around the center of a circle with a 200 micrometer radius and 20 Hz frequency. You can see that the adaptive filter controller provides much better performance in the moving target tracking case than the conventional PI controller. This figure shows the root mean square error of the laser beam with the conventional PI controller and the adaptive filter controller. This figure shows the trace of the laser beam. These figures show how effectively the adaptive controller improved the control performance.
Yeah, here we are showing a adaptive optics test bed and I will show you the results. And again, it becomes quite impressive because we do get a lot of VIPs coming to our place. And I think that is the important part. You want to demonstrate something they can immediately see. So here it is a distorted image. And then you can see that you do not get a clean. And here wavefront error is almost 5.3 or so. And then you put the adaptive optics and this becomes a point source and you can see the image. So it is quite nice. You put the adaptive optics on, suddenly the image improves and then people get impressed that we know what we are doing. So that is an important part. So we actually spent a lot of time to get all these test bags, and we got a clean room because optics can get dirty. So you want to have a clean area, so you don't get And you can see that we got a big, many labs. Now, one area in the last I want to is correct of the beam aberration due to atmosphere. So when you have a laser beam going through the atmosphere, then basically you have a moisture, you got a temperature gradient, and it changes the reflective index. So reflective index is changed. So the laser beam which is played, it gets distorted, and that is where you use adaptive optics to correct it. So here you can see you got a plane wave coming, and then you got a variation in the index of refraction, and instead of the plane wave, it gets distorted like that. So you want to use the adaptive optics to correct it. And just few slides, and that's where
atmospheric disturbances, they will be creating certain worst cases for adoption. All cases are equally handy.
No. There are actually, that is where the challenging part is if you go through the atmosphere for a short time or long time. So here you can see exactly that if you are going only 100 meters, then your laser beam is not too much distorted. If you go 1 kilometer, it gets distorted. If you go 5 kilometers, then it's really bad. So depending on how far you want to go, that's where you decide whether you want to use adaptive optics and so on. And that is where if you have a horizontal path, that's where deep turbulence and all that becoming very critical. So right now the project US and India is working on is like a long distance. And that is the area I think DRDO is very much interested. And this is the test bed we have at our place. And you got a telescope and it has 2 gimbals and you got some target. So you basically got a wide field of view camera, so you can come into the target field of view. And then you got a narrow field of view camera. Here you basically find tracking. So laser source beam is going through all that path, and then this one gives you the fine pointing, and then it should go where you want it to go. So there are again a lot of controls and structures and optics and quite expensive. These facilities are quite expensive. We're talking about millions and millions and millions. Maintenance is also. So I think in summary, adaptive optics is a multidisciplinary area. It is covering optics, mechanical, electrical, controls, and so on. So that is where, and has many applications like a ground telescope. It is now almost standard to use adaptive optics. Imaging satellite, that is the area started getting interest. In the laser beam control, communications, laser communications, and high energy lasers. And so I think we showed you some of the tests that we have in adaptive optics at our Center of Excellence, and that is the one advantage that getting a Center of Excellence was quite a challenging. You have to do marketing, which I hate to do that, but that becomes part of, at least in America, professors, they have to bring a lot of money for their group. But it happened, and you do get some people jealous of you, that how come you got it, we did not get it, so that's a part of that. Okay, well, thank you very much for your attention coming at this late hours.